So any questions before we get started? Excellent. I did hear that. So it's locked in, and you guys probably had a weekend like I had a weekend. It's reasonably productive. Just nothing work-related productive. I'm getting too old for that, unfortunately.
Saturdays. Lost a lot of water Saturday.
Ladies, how you doing? What's that?
There's all yard work. Terrible yard work. Yeah, yard work.
That's what caused me to drink a lot of beer.
There you go, you can't drink water, that's a damn
You can't garden without a buzz on, you know?
Reminds me of the old days. Basketball out in the sun with tequila drivers.
That's amazing.
Old days.
Those guys when you make it rain with a grease, huh?
Yeah, exactly. No, I was a post-up.
One shot, two
You were
shots.
a center?
No, I didn't say I was a seven, I said I was a post-up guy.
He's an outside post.
That gas
blocking.
pushing out there, you know,
Okay.
Okay, so. Okay, so where do I want to start here? Let's talk about forces on, magnetic forces, excuse me. On moving charges. So we've talked a little bit about the basics of magnetic fields, but functionally, as with most things, how do you know there's a magnetic field?
Stick something in there to react with it.
You gotta have something that will magnetically interact with it. Usually it's a moving charge, it could be another magnet, could be a wire with a current in it. Bottom line, you need something to know it's there. So if you take a charge moving at some velocity and it enters a magnetic field. I'm going to use dots to indicate a magnetic field that's pointing out of the board. And we can give it a value or not, but let's just call it 3 Tesla. As the charge enters the magnetic field, so I should put some more here. But while, I should say, the charge is in the magnetic field. The magnetic interaction between the moving charge and the magnetic field, perpendicular to both the direction of the magnetic field and the direction of the movement of the charge. So, for those of you who are looking for a reason to apply vector calculus or see something in 3 dimensions, once you get to magnetic fields, it's all there. So, within the magnetic field, easiest way to think about it is take your fingers and put them in the direction of the moving charge. Curl your 3 fingers, other than your index finger, in the direction of the magnetic field. Direction of your thumb is the direction of the magnetic force.
You said the outer board like this?
So if you've got a charge moving in this direction and you got a magnetic field pointing out of the board, thumb is going down, you'll have a magnetic field, or I'm sorry, a magnetic force that will be perpendicular. So it's kind of like whatever the direction, or whatever the plane of the direction and the field, the magnetic force will be normal to that plane. And don't use your left hand, you need to use your right hand at least for positive charges. If this happened to be an electron though, you could use your left hand. But to calculate the magnetic force, we would take the magnitude of the charge and multiply it by the vector product of the charge velocity and the magnetic field. So here's our cross product we haven't seen with much application since chapter 10, chapter 211. But we might just note that this is the equivalent of this expression here. If you didn't want to do the determinant and lay them out and chop up the cross product, what you can say is that the magnitude of the magnetic force is related to QVB times the sine of the angle between V and B, and the key is from B going into V, or I'm sorry, from V going into B. And then the direction is in the plane of Q and D, or D and B. So, according to the right-hand rule. So, you can do a direct calculation without necessarily having to do the full cross product. Either way it works. So, the interesting thing about this, though, as that force interacts with the charge and causes that charge to change its direction, and notice that the interaction between the force and the motion, or not the interaction, the orientation, it's 90 degrees, because it's in a plane of V and B. As the motion changes, or as the velocity, well, first of all, the force does not affect the speed. It only affects the velocity by direction because of the 90-degree orientation. As the velocity changes direction, so does the magnetic force, because it always stays oriented according to this cross product, which will mean it will always be at a 90-degree angle to the plane of V and B.
So, if you were to draw another, like the next moment, suppose.
I'll draw a moment that's not quite so next, but yeah, say out here somewhere,
Right.
as it's moving along.
You're still gonna have that magnetic force directed downward.
No.
Because it's gotta be.
Once the
parallel,
velocity
perpendicular to
changes,
both.
once the velocity changes, now the magnetic field, or I'm sorry, the magnetic force.
Right.
So there'll still be a 90-degree angle between V and F, and also a 90-degree angle between B and F.
And the magnitude of V is still the same?
The magnitude stays the same because no component of the force is along or parallel to the direction of V. So there's no component of force that can speed it up or slow it down. All it can do is alter direction.
So wouldn't it just move in a circle? Whatever it is?
That's the only thing it can do. So the net result is that you get, and that's one hell of a circle, isn't it? Forget about that. So the consequence is when you have a magnetic force interacting with, and this is for a 90-degree angle, if it's not 90 degrees, then you have more complicated motion. But at least for the simplest case, where you have a 90-degree orientation between all three components involved, V, B, and F, then you'll get a uniform circular motion with a characteristic radius of R. So, okay, so for the simplest case, when you have this perpendicularity, then the magnetic force, the magnitude of it, will still be related to QVB, but this will also correspond, well, I'm going to do it in terms of Newton's second law. We could say that the magnitude of the net force then will only be related to the magnitude of the magnetic force, and this should be equal to MA. And I'm using magnitudes here because at every moment everything will change, because the direction is going to continuously change. So we only have FB. And that's typically the case because most moving charges are moving so fast that the interaction with G is always nominal. Almost always nominal. So we just start applying things then. And for this type of motion, we end up with an expression that looks something like this. The magnitude of magnetic force will correspond to the only force generating the net centripetal force for this circular motion. So this is a good expression to be aware of. And the point being is, for this circumstance, you have the uniform circular motion requirement. So, given this information, then let's just ask, let me have you guys think about a question. What is the equation? What the hell? What's the angular frequency of this motion? I want the equation. I don't want the actual value. I can give enough information. I might ask yourself, first of all, when you have uniform circular motion, how is the angular frequency related to the velocity? So, change colors here. Once you know that, then it's a matter of just plugging in for V. And by the way, it would be,
Yeah.
do I have it backwards, or is it R cross?
No, it's omega
I
cross.
think it's omega cross R. For a 90-degree orientation, then this reduces to Actually, I shouldn't even bother with that, I should have left it in the other side, didn't I? Yeah.
Real quick, those are the same V, right? V versus mv squared over r.
Oh, yeah.
Okay.
Yeah, that's the velocity. This is not voltage. We're gonna put a voltage in here in a moment, figure out how we would speed some charge up to begin with. But in the meantime, what should this expression look like?
It's R QB. Right? Oh, sorry, no, QB over M.
Is that consistent? So what do we have here? We would have, is it gonna be inverse to R? You have an omega R there, and you're gonna have omega squared, R squared, so one of the R's cancel out, so it's gonna be Q B, and it's gonna be inverse to R.
You're trying to solve for omega, right?
We're gonna have them backwards, yeah, I got them on the wrong side. So QB over R, because the omega is gonna be on that side, and the M is gonna be inverse.
Just leave the V over R and solve.
Well, first of all, just get rid of one
Yeah,
of
and then you have V
those.
over R divide the M out, right? V over R is omega,
Yeah,
so it's QB over M.
you got two R's here.
We have two V's.
Oh, one of them goes away, never mind. Sorry. You all right? Does that make more sense? Okay. So this would be the angular frequency of the precession as basically this magnetic interaction occurs. It's inverse to M, which is kind of interesting, but why might it be inverse to M? What is M? Well, it's mass, but what else is M? It's a way of...
Charge.
It's not charge, it's the inertia. So you would expect the frequency to be slower for a larger amount of mass. It'd be faster for a larger Q and a larger B because they're directly related to the forces involved. But it'd be inversely related to the mass. So I just point that out because at least it's consistent conceptually with what one might expect. It goes slower, circularly. So let's then consider the question. Here we go. Goblay. I'm having a day. A electron. There we go. My grammar's just getting better and better.
That East Northern accent.
That's where I got it, you know what I'm saying? Talk to the farmers. Hey, farmers, how you doing? They say, you're doing good. You doing good? Yeah, you close proud. Produce is good. Flowers of the field, yeah. Jesus. Ah. So we'll do something like this. We're going to put an electron right here, and we're going to put it in a electric field. Just to mess with you. It starts from rest or anywhere close to rest. So it's in an electric field. And that electric field occurs, okay, so
Accelerated.
accelerated, yes. I know, I'm dying. no, that's okay, I'm, like I said, I'm having a day. Okay, so we have 1,000 newtons per coulomb in a horizontal direction. Let's give a coordinate, I want to make you guys coordinates, it's not really a coordinate system. So we'll put it in the I direction, okay? Negative V. And the length of this, I'm gonna make you guys work for some of this. Length of this is 0.05 meters. As the electron accelerates through, it enters magnetic field.
The magnetic field is outside of that little.
Yes. I don't want to make it any more complicated. So it enters a uniform magnetic field. I put 3 over there and didn't bother to use it, right? So out of the board. So let's ask some basic questions and okay, so what is V as it enters the field?
It starts from rest.
Yeah. So what's the magnetic force as it enters the field? So this will be a vector, at least initially. Where does it exit the field? Assuming the field is large enough to account for its entire path. It starts here, it's going to produce a half circle and come right back out, right? How long is it in the field? Good way to start it. And we can note that the mass of an electron is about 9.1 times 10 to the negative 31 kilograms. You should know what the charge of an electron is, but it's negative about 1.6 times 10 to the negative 19 coulombs. And we know what the magnetic field is, etc., etc. And I will say, as a corollary to the first step, you might just ask yourself, what is K as the electron exits, or enters, I should say. You answer that question, it becomes a relatively simple problem. Put this in here initially to give some reminders. To remind you of some important things. because so much of this stuff is intertwined. It's an electron, right? So the only way it's going to accelerate forward is if the field is backward. Let's sort of point that out. So an electric field does work on a charge. How do you calculate it?
Use some work energy.
You can use the work energy theorem. We can go back to the
Yeah.
kinematics, right? You've got a distance, you can calculate the acceleration, you can do all that. Or you might just say that the change in kinetic energy should be related to Q delta V, or V if you will. And to get delta V, we would integrate E dx in this case. So this should go as Q E delta x. And there should be a minus sign in there, no question about it. That's why I'm just looking at magnitude for now. Since I'm going on video here, I should probably put all the pieces in together. E is a negative number, I guess, as a vector, but yeah, you just write it as a magnitude. Yeah. Being a little bit sloppy because I'm not trying to overthink the problem.